Okay, so while this problem may not look it, this is pretty much going to be the most involved problem in all of Chapter 7. I'd like to do at least one example like this, but I wouldn't worry too much about it for your exam. So the thing is in this problem, it doesn't look like that much, but you notice how we have an input voltage here and it looks like this. And so the thing is, it starts out at 0, it then gets switched on to 9 volts, but then after 0.3 seconds it gets switched back off. So that means there's in fact 2 switchings that are happening here, and we're going to have to go through our whole Chapter 7 process for each one of the switchings. Okay, so start out here our normal way. We're going to have t equals 0 minus. We draw our circuit, so it's 0 minus. The voltage there is 0. We have our 6 kilo ohm resistor. We have our capacitor has been in position for a long time, so it is an open. And again, we always want to find the voltage across the capacitor at 0 minus, which is the same as the voltage across the capacitor at 0 plus. And so the thing is that if you look at what's happening before the switch happens at 0, there's not any power being put into the problem. And so what that means is there's not going to be any voltage stored across the capacitor, so that means it's just going to be 0. So it's actually pretty easy at 0 minus here. Next thing up, we're going to look at 0 plus. So that means the first switch has happened. I now have a 9 volt source here. Still have all the resistors. Since something changed in the circuit, we get our capacitor back. And I know that the initial voltage across the capacitor is 0. And what I want to find is I want to find the V0 of 0 plus over here. But notice that the capacitor is in parallel with this. So if you were to do this, you'd have to have KVL, that the voltage across the capacitor has to equal the sum of the voltages across the two resistors. But the voltage across the capacitor is 0 from what we've solved already, which means the sum of the voltages across the resistors is 0, but they're going in the same direction here, so you can't have a negative cancel out positive. And what that means is the V0 of 0 plus is also 0 volts. So that gets us our initial point there. And then remember what we're supposed to do is we're supposed to say, okay, well, what happens if we go to infinity? But we have a problem here. Because we're right here, we're just a little bit past 0. We want to see what happens at infinity. And as far as we know right now, the 9 volt source is hooked up there. It's going to stay there forever. And so really, this is the fake infinity. This is the infinity as if the 9 volt source had never flipped off again. Because as we're moving here, we don't know it's going to flip off until after it happens. And that's going to be a separate part of the problem. So we'll say, okay, T infinity and fake, where it goes on forever. We're going to get our 9 volt source. As I said, we're going to assume it's there. We have our 6 kilo ohm resistor. After a long time, we have an open circuit here. And then we're going to have our V0 of infinity here. And this is actually going to be a voltage divider. So V0 of infinity is going to be the total voltage times the resistance you're at over the sum of the resistances here. And so that's going to be 4 volts, which is our K1. And remember, our K1 plus our K2 is the initial value of this. So that means 4 plus K2 is 0, K2 is 0. And the last thing we need to do is we need to find our R Thevenin to get our tau. Well, in this case, from the point of view of the capacitor here, the 4 and the 8 is 12. That's in parallel with 6. Let's see here, 72 over 18 is going to be 4. So 4 kilo ohms times the capacitance of 100 microfarads. that is going to give me this of 0.4 seconds. And so what we'd have is we'd have the formula V0 of t is 4 minus 4 e to the negative t over 0.4 volts. But the problem is this is only good up until the point where it switches again. So I'll go ahead and write that on top here. V0 of t is 4 minus 4 e to the negative t over 0.4. And this is good up until it switches a second time. So now that we have that information, now we're going to do the switching problem at 0.3 seconds. So let's make some room here. And what's going to happen is instead of looking at 0 minus and 0 plus, we're going to look at 0.3 minus and 0.3 plus. And the reason why is, again, because when you have a circuit, and if it's switching there, then you need to look at the switching time. And normally it's been 0 for us, but there's no reason why it can't be something else. So if I put 0.3 minus, then that means the 9 volt source has not switched off yet. Notice that I can't erase the capacitor here because it has not been happening for a long time. But what I can do is I can find V0 of 0.3 minus by using my formula up there. And putting that into my calculator here, I get 2.11 volts. So that means I know the voltage here is 2.11 volts. That means I can find the voltage across this. Now I could go ahead and find the current first and then do Ohm's law, or I can just notice that they are in series, so they're the same current. And this one's half as much resistance, so it's going to have half as much voltage. And so 2.11 divided by 2 is going to be, say, 1.06 volts. And once I do that, then now I can look at, KVL here basically, and find that the voltage across the capacitor at 0.3 minus is the voltage across the capacitor at 0.3 plus is going to be 3.17 volts. Once we have that, then we go ahead and look at 0.3 right after the switch. The source goes to 0. I have my capacitor here. And I know that the initial voltage here is 3.17. And if I know it's 3.17, well, then I can, think of that as a voltage divider across this part, and I can find my V0 of 0.3 plus. And the thing is, if you just kind of look at these two circuits here, it's going to work out the same numbers. It's going to be 2.11 volts. So we're good there. Now we need to what happens as we go to infinity. So infinity, the source has been turned off for a long time. My capacitor is in open. Again, though, nothing's activating the circuit, so V0 of infinity is going to be 0, which is your K1. So V0 of t is going to be K1 plus K2 e to the minus. Now there is one small difference here. When you're changing at a time that's other than 0, you don't just do minus t over tau, you do minus t naught over tau. Okay, well, V0 of 0.3 plus is 2.11, which is K2 e to the minus 0.3 minus 0.3 over tau. That gives me my K2 is 2.11. My tau is the exact same thing it was before, because you still have the same R Thevenin in this case, and you have the same capacitance. And so what we can now do is we can write down our final answer as a piecewise function. And it would be v0 of t. It's 0 for all the t's that before the switch happens. It's 4 minus 4 e to the minus t over 0.4 for the part where time goes after the first switch, before the second. And then after the second switch, we're going to get the following here. And so this then gives us our answer. As you can see, having it with two switches, it's not that much different than before. It's just twice as much work. I've had to solve problems before that had like 3 or 4 switches. It's just no different concept-wise, just longer and longer and longer. So for your exams, I'd really only worry about ones with one switch. I just wanted to show you how it would look like with a 2-switch problem here.